Uh, we continue from here, integration by partial fractions. As you would see here, these are lecture notes from 2019 full again. F of x is a rational function. We want to integrate that. Rational function means p over q, p and q are polynomials. For the case 0, the partial function is p over q, where the degree of p is bigger or equal to the degree of q. We do the long division, that's the technique. Case 1, p over q, when q has the product of distinct linear factors, like for example q x minus 3, x plus 2, minus x plus 9. This is case 1. Case 2, p over q, where q is the product of linear factors, some of which are repeated. For example, this q, x plus 4, this is not repeated, but x minus 2 repeated twice, x plus 1 repeated 3 times. So this is case 2. Case 3, p over q, where q contains some irreducible quadratic factors, none of which is repeated. For example, x squared plus 1 is an irreducible factor. You cannot reduce it to linear factors. X squared plus 4 also irreducible quadratic factor. But on the other hand, x minus 2 is a linear factor. So how would you do? This is case 3. Case 4, p over q, where q contains repeated irreducible quadratic factors, which means x squared plus 1 repeated twice, x squared plus 3 repeated 3 times, x plus 5 is a linear factor. This is case 4. And let me see. Okay, case 5 is the rationalizing substitution. We are going to talk about this later. Let's do some case 2, because we already covered the previous cases. Case 2, when it's p over q. Okay, actually this case 2, in this case, contains case 0 as well, degree p greater than q. If sometimes other cases may contain case 0. In this case, this is the situation. So we do the long division first to make it simpler. This divided by this, you get x plus 1 plus 4x over x cubed minus x squared minus x plus 1. And then we do the integration, integral of x plus 1 dx, integral of 4x x cubed minus x squared minus x plus 1 dx. We call this j. So our integral I is this plus j. Okay, so we need to find j. J is in the form of p1 over q1. It's a rational function again, of course. Okay. What is q1? Q1 is x cubed minus x squared minus x plus 1. Can you factor it out? We factor out x squared, I get x minus 1. We have another x minus 1 here. Factor it out. We have x squared minus 1 and x minus 1, x minus 1, x plus 1. X minus 1 repeated twice, linear factor. So how would you do? As we said at the very beginning, for each repeated linear factor, you would just put a over x plus 1, b over x, here. Okay, this is not repeated. X plus 1 is not repeated, x minus 1 is repeated. So b over x minus 1 plus c over x minus 1 squared till you exhaust the powers of powers until 2 actually in this case. And then we are going to equate the denominators. 4x is equal to a times x minus 1 squared, b times x plus 1, x minus 1 plus c times x plus 1, and then factor it out, and then expand the terms, equate the like terms. This is 0 times x squared plus 4 times x plus 0 times 1. So x squared is power coefficient 0, so this is 0. X is coefficient 4, constant term is 0. We put them all three equations in here. A plus b is equal to 0 implies b is equal to negative a. So I put it in, I use it in the third one, and I get 2a plus c is equal to 0. And I combine these two boxes, the equations in two boxes, And from here I got c is equal to 2, a is equal to -1, and b is equal to 1. I'm assuming that you can solve this system of equations. And then integral j is equal to, j is equal to integral 4x x minus 1 squared x plus 1 dx. And now we have the -1 over x plus 1 dx, 1 over x minus 1 dx, and 2 over x minus 1 squared dx. I'm gonna call it k, the others are okay, easy. I'm gonna say, for k, I'm gonna say u substitution, u is equal to x minus 1, du is dx. I got 2 times d over u squared integral, and 2 times antiderivatives, negative u inverse, negative 2 over x minus 1 plus c1 is the k. So my I at the beginning is x squared over 2 plus x plus j, but j is negative ln x plus absolute value of x plus 1 plus ln x absolute value of x minus 1 minus k. Okay, k is this, minus 2 over x minus 1 plus c, and we are done. Okay, because for j the first 2 term is okay. Only the k was a little bit problem. I wanted to clearly explain it. This example is a case 3 example. This is again p over q, polynomial over polynomial. We look at the q, factor it out. We have x squared plus 4. X squared plus 4 is irreducible. And then what? Then p over q is equal to a over x plus bx plus c over x squared plus 4. This is what the theory says. And we equate the denominators, a times x squared plus 4 plus bx plus c times x. Okay? Combine the like terms, equate the coefficients. You get x squared is the coefficient a plus b, it has to be 2. X is coefficient c, it has to be -1. And constant term is 4a, has to be 4. From here, c is -1. A is 1 and B is 1. Perfect. We put back in what they are. Okay, this is dx over x plus x minus 1 over x squared plus 4. This is j. The first one is okay, and I want to call it j. For j, be careful. I do this trick, multiply and divide by 2, and I use the substitution, and I'm good to go. By the way, I should say I separated x and -1. I separated first, and I look at the first one. The first one is by substitution. Second one is inverse trigonometric functions may be useful. Trigonometric substitutions could be useful. Let's see. Here in the first one, the substitution box is u is this, and du is 2x dx, and I have 2x dx here. Everything is perfect. J is equal to 1 over 2 du over u minus, I call it k. And the first integral is 1 over 2 natural log of absolute value of u. And what is u? U is x squared plus 4. It's okay, minus k. But what's k? So let's look at k. K is a new integral for you. You remember x over a thing and inverse functions, inverse trigonometric functions, and here we are. Integral dx over x squared plus a is going to be 1 over a arctangent x over a plus c. We discussed this before, and this is going to be 1 over 2 arctangent x over 2 plus a big C. We forgot to put a c, but we will put it later. Here, we put it here. Okay, so this is our final answer. Case 4, it's again p over q. Terms are, the factors are linear, but the irreducible factor is repeated twice. So how would you do? The theory says for the linear factor you write a over x. For the other guys, for the repeated irreducible quadratic factor, bx plus c over x squared plus 1 plus dx plus e x squared plus 1 squared, till you exhaust the multiplicity of the irreducible factor. Again, we equate the denominators, we gather the like terms. X to the 4 has coefficient 0 here because we don't have x to the 4. A plus b is 0. X cubed has a coefficient -1, c is -1. X squared has coefficient 2, so this is 2. And x has coefficient -1, so c plus e is -1. And constant term is 1. And then I have 1, 2, 3, 4, 5 equations and 5 unknowns, and I can solve it. C is already solved, A is already solved, B can be solved from here at -1, A is solved, B is solved, D can be solved as 1, C is solved, E can be solved as 0, and I put them in here. Now I look at the terms. It's 1 over x is okay. This is, I have to separate it like I did before, and this one substitution should work. So I have I is the one I wanted to find, ln x plus, I call it j and k. I will deal with j and k separately. J I separated like I did before. Substitution works here. -1 over to ln x squared plus 1 is fine. And this is arctangent x because a is 1. Plus c1. For k, we are going to do the substitution. U is x squared plus 1. du is 2x dx. We have the trick, multiplying and dividing by the same number. K is equal to 1 over 2. Du over u squared because 2x dx is du. X squared plus 1 squared is u squared, and this is 1 over 2. The antiderivative is -1 over u. -1 over 2 times 1 over u plus a constant. What is u? U is x squared plus 1. We put back in. This is our k. I put the j back in and k back in, and this is my I that I want to find. And last example, I think, rationalizing substitution. Your integral may have some irrational expression like square root of something. Like in this case I do. So I want to rationalize the numerator by substitution. I'm going to say, how can I make this rationalized? I can let u to be this and square both sides, and I have x plus 4. And x from here is u squared minus 4. And 2u du is dx. And I'm going to convert everything into u. Let's see whether it's going to work or not. Okay, so this is dx. This is u square root of x plus 4. And this is what? X. And see, this is polynomial over polynomial. So whenever you have irrational expression, by using a proper substitution, you can convert it to a polynomial over polynomial expression, which then we may need to use the partial fractions to get it. This is u squared over u squared minus 4. I can do the long division just to see it, log division, or I can do the trick. Log division is fine, or you can do the trick, which is you are adding and subtracting 4 from here, which is going to make the denominator the same. So that you are going to get 1 from here, u squared minus 4, u squared minus 4, you get 1, plus 4 over u squared minus 4. Alright, so then, so this expression I becomes 2 times integral 1 plus integral 4 over u squared minus 4. I'm going to call this j, and maybe I may need some here. I'm going to do the partial fractions here. Okay, it seems so. And I factored out the denominator. This is u over a over u minus 2, b over u plus 2. Equate the denominators, gather the like terms. There's no u term here, so coefficient is 0, a plus b is 0. Constant term has to be 4. Okay, and then solve it together. I get a is 1, b is -1. I write it back in, and then natural log. The integral of this is natural log of absolute value of u minus 2 minus natural log of u plus 2 plus c1. I put back in what u is in terms of x, and I get my j. So I is equal to 2u plus j, but what is u? I put back in u. U is square root of x plus 4 plus natural log of this expression. I use the properties of the natural log. The difference of the natural logs is the natural log of the ratio of the two plus c, and you get the answer done.